Everything sound okay? Okay, welcome to the end of the week on a rainy day in Davis. There's a new assignment out there for you which says do something. Okay, your choice. Do a complex something. We have had people here on a musical instrument type thing. That's one of the things I usually give. You can do your choice. There's some other things. I've had some people. There's some good things here at UC Davis to do. You can look up the Meyer sundial if you want. James Meyer's wife had a sundial, which is over. I think it's over by Kerr Hall. That you can do, which is kind of interesting. You can do one of the eggheads if you like. We've seen those come through before. There's 10 eggheads around campus, and I think the most famous egghead is the one outside of Marac Hall, which is the egghead that's committed suicide by jumping off the administration building. Okay, then there's the other two famous ones are the ones the one most people see are the one in front of the library that's in the book. There's two others over by the law building, and they're sitting on these two knolls, right? And they're debating each other, and they do not have any ears on them, right? But they're obviously debating, and it's very appropriate for the law school to have them there. But if you want to do anything else, just let me know, okay? Come and talk to me. The one thing that is not allowed is that someone made for fun a 1/4 a basic rectangle in the middle of the screen, textured it with a picture of a guitar, okay, and said, "Here's my musical instrument." Okay, that's a little less than what I desire for this course. Okay, think about it. This shouldn't be that hard of a project after you've gone through the Kemper thing. The one thing that you have to add to it is texturing somehow. So you got to get the wood grain on the 12-string guitar or whatever, okay, in order to do things. Go ahead.
Can we get extra credit for objects like super complex?
We'll talk to me about that afterwards, okay? Talk to me about that afterwards. No, talk to me about it afterwards. Okay, we'll see. And today at 3, there's Sebastian will be holding a discussion for you in here. I've told him he can't answer the question on the exam directly, right? He's not to answer questions of how do I answer number 7. He can't answer that question, right? But he can answer. He can maybe give you a different matrix and say how he would do that, etc. So. He will go through the exam. And prepare for this exam, please. Okay? A lot of people say, oh, those questions look really easy. I can whip those out and I don't even have to think about them. No, please prepare for the exam. Okay? We find out you don't do very well if you prepare that way. So do that. And so the exam will be on Monday during this time, right? No, and don't ever ask that of a... Ken's recommendation is you don't ever ask that of a professor, right? And I'll tell you a quick little story. I had an office mate, a very nice guy at the University of Colorado, and we had a German professor teaching us this class, and he said to us that he didn't know how to give exams in the American system. How do you give exams? And Clark behind me said, "Oh, why don't you just give us a take-home, right? Take-home exam." And I, those of us in front of him nearly shot him. I mean, but he's like, "No, don't." Oh, what a great idea, the guy said. And so the next day he came back in and he said, here's 21 problems, right, that we scripted up. And we all know that these problems are true, right, that you can do them, right, but nobody's ever published them before, right? Do them, right? And I basically stopped working in my other 2 courses at the time, and didn't do anything in them for the rest of the semester. I only worked on those 21 problems. I think I got 9, and mine was the second high score, right? Ray Faybeck, who's at LSU, he's a professor at LSU right now, got 16, and I don't know how he did it. I still today do not know how he did it. It was probably the most difficult exam ever, so I've always said to students, don't ever say open book, because it means a professor can ask anything, right? and you don't want me to ask anything. You want me to ask what's on that little sheet of paper I gave you, right? That's what you want me to ask, because I've told you I'll do that. So, okay, so anyway. So today I'm going to do Zbuffer shadows. Right? It won't take long to do, but these are kind of cool. And they work, right? People use them. There's difficulties with them. Lots of people use them because they can fake some fuzzy shadow effects, some things like this with them. But there's difficulties with them, and they have to be tuned kind of nicely. There may be still, I don't know if there still is, an OpenGL function that will allow you to do this, okay, that's out there. But it's difficult to do, and I'll show you some of the difficulties as we go along, okay? The idea is really simple, right? It's a very simple idea. And the first paper on this was published in, I think, about 1978, right? There's been 2 ice ages in this field, one about an ice age change, one about 1980 when bigger machines came along. We were able to do bigger things. And one about 1994, 95. Netscape version 1 was 1994. Okay, that's all of a sudden when web and other things came along. We actually got bigger machines, could do many more things also. But this is about 78, was first proposed, and it was proposed by a guy named Lance Williams, who still works around Pixar somewhere. And basically one picture was produced, and then it kind of went away, and it came back about the late 80s, and kind of went away again. It kind of came back again. It's gone away again now. So people keep trying to resurrect this thing, but it's got some interesting difficulties. Now, the way you do this is actually pretty simple. The idea is you've got a viewpoint that you're looking from, an eye point, camera point that you're looking from. And you can create an image space from these camera points, right? We all know how to do that now. You also have a light source out here, and maybe several light sources, but let's talk about just one at first. You have a light source out here. And the thing about the things from that light source is that the things in shadow from a light source are the things that, if I took a picture from the light source, would be the things I couldn't see. Right? If I put a camera at the light source and took a picture of my object, it'd be the things I could not see from that point that would be the things in shadow. So if I can see the things, they'll be illuminated. We can do the other ones, right? If I can see them from the light source, they're going to be illuminated. And so when I look at from the light source here, I can take a camera and I can determine those things that would be illuminated, right? But then what I have to do is, when I look from my eye point into the scene, right, I can look at these objects. I have to figure out which of those objects are illuminated and which of them aren't. And so I have to kind of reconcile these two camera things. Okay? So number one, the first thing to remember that, for each light source in this thing, there's going to be a rendering step. We're going to take a picture of, right, our scene from each light source. Right? Then we're going to take a picture of our scene from the real eye point, and then we're going to reconcile the views together. Okay? That's the way these things work. So, right, from each light source, create a picture. All right? And then 2, right, from the eye point, create a picture. I'll tell you what that means. And 3, then reconcile. To create the end. Okay? Now, I'll wave my hand at the reconcile part too, which isn't too bad. Suppose I have a camera with an eye point going in here, and I have a camera out here looking down at the scene from the light source. Okay? Now, each one of these cameras I'm going to get an image space. Right? And I'm going to have to reconcile these image spaces back up. And I can do this because to get an image space, what do? You apply a camera transform that gets you down to the origin looking at the z-axis. Then you apply the viewing transform, right? And that gets you into image space. Right? Oh, there's a divide by W step in there. I'm not going to do that, right? So I'm going to get these x, y, z, w's down here. Right? Now I can, if I have a transform that gets me from the point of the light source and the vector, if I have a transform that gets me to the vector and the point at the camera, if I can transform these guys around, and I can, what I can do is take the points in my image space here, hit them with the inverse viewing transform, the inverse camera transform, the transform that gets me over here, the new camera transform, and then the viewing transform there, and I can get into the image space for the other camera. And it's all a 4x4 matrix when I'm done. And the idea is I can get between these two image spaces using 4x4 matrices. Okay? And that's what I'm going to do with this reconcile bit. Now from each light source here, when I say create a picture, what we're going to create is a Z-buffer. In reality, we're going to create a Z-buffer. It's going to be a little bit of an expanded Z-buffer, but it's going to be effectively a Z-buffer. Okay? And each time it makes sense because the Z-buffer holds the values of those points that are actually visible. Okay? When you do things. And so same thing here. I'm going to create a Z-buffer here. And then I'm going to reconcile these two Z-buffers. Right? So that's what I'm going to do. So here's a general picture. Right? So here's my viewpoint coming into the scene here. And here's a light source out here coming in. And you get this transformation here that goes between these two things, right? I'll call it transformation, I'll call it T. Now with this eye point here, we have a camera transform and a viewing transform, which are these 4x4 matrices. I'll put this around T because going from one view here to one view here gives you a 4x4 matrix. And then over here, to determine this thing, I'm going to get another camera transform, C prime, and another viewing transform, V prime, to get down into my image space for this view. Okay? So what I'm going to do is to get from if I have a Z buffer here, I'm going to take the inverse of this, that transform, then this, and I can go back and forth as much as I want between these two. And the whole idea is going to be going back and forth here. I can reconcile these two these two Z buffers as I go through. Okay, that's kind of the picture of what I'm going to do. And I can do this, if I have more than one light source, I can do it for more than one. Okay? Now, so create a Z buffer. So what I'm going to do here is, over here I have this camera transform, 4x4 matrix, this viewing transform. Oh, by the way, the viewing transform is the one that was, it had cotangents in it, right? F plus n over F minus n, 0, 1, 0, 0, 1, 0 in the fourth column. That was this one. It has an inverse matrix. It's actually out there on the notes. It's actually something you can calculate the inverse of this matrix probably in about 15, 20 minutes yourself. It's almost all zeros and ones, right? You know, so it's actually easy to do. I mean, the inverse doesn't have cotangent up here. It has tangent up here because cotangent times tangent is 1, right? And when you want the inverse to multiply times real matrix, you want the identity when you get done. So what I'm going to do is create a Z buffer here. And if you take these matrices, if you remember, x, y, z1, you multiply these times x, y, z1, and you get out an x, y, z, w. Like this, right? Which we're going to convert to x over w, y over w, z over w. Okay? And then what happens in our Z buffer? If we have this point x, y, z, right? right? What happens in our Zbuffer here is that we're going to take a polygon here, and we're going to do what we call scan conversion on this polygon and figure out these points. Each one of these points is going to have an XYZ value, okay, to figure out what points are actually in these things. And then in the Zbuffer, what we do is if something is clearly in front, we keep that element in front, correct? Now what we can do is, all of us figure out interpolation schemes so that these points aren't just, the way I presented this is that we get interpolation schemes where these points have X, Y, and Z's. You can actually do it too so they still have X, Y, Z, and W. Okay? You can interpolate across so they have X, Y, Z, and W. Okay? Everything works just fine. And so what happens is that each one of these points here in your Zbuffer will have an X, Y, Z, and a W. Right? The Z and the W you have to keep around. The X and the Y are going to depend on the pixel, on the position in the screen. That's easy to do. The Zbuffer normally keeps just the Z around. We have to kind of keep the W around also. Okay? But what we can do then is we had this point X, Y, and Z. We can reverse this step, right? And we can pull this back using this one inverse and this one inverse. Okay? And then we're back in normal space with this actual point. And the idea is to get this point back to normal space again. And you can do it with the inverse matrices. You have to keep W, you can't divide by W first. You have to keep W around. Okay? Because if you divide by W, you lose it in some sense. Okay? So you have to keep W around, but you can track this back into normal space. Once it's in normal space, we can transfer it over into the light source and project it down into another one. Okay? Or vice versa. And the idea is to create these Zbuffers, right, and then use the transforms to transform them back to one of these other spaces. Okay? And now it looks something like this. So here's the Zbuffer here, right, and I suppose I have some objects in here. Okay? And from the light source, right, I have another Zbuffer over here. This is hard to wave at here. I have another Zbuffer, and I have this point here, somewhere in the Zbuffer, that says I'm in front. Okay? What I'm going to do is I'm going to take this point back to normal space by applying first I'll call it V prime here, V prime inverse, and then I'll apply C inverse, right, to get me back to normal space. And then I'll plot this point down to here. Okay? That I can do this. And I can plot a point here, alternately, right, back up out of this space and somewhere into here. Okay? And once I got this correspondence going, that I can plot these points between these two buffers, between these two image spaces, now I can do some work. So let me take a point here. Say I determine that this point is in front. And I can plot it back using my 4x4 matrices and come back down here, and I can plot it into the Zbuffer here. Okay? Now if I blow this thing up a little bit here, what I'll see is that the point that I'm plotting in here lands maybe there. Okay, it won't land. I keep each one of these Zbuffers keeps the values here. At the corners, right? But when I plot something back from this one, it's not going to lie exactly on the corners. It's going to come in somewhere here. And now the thing is, to determine if this point's in shadow or not, right, I have an XYZ for this point here. I have an XYZ for this point. And X and Y have to do with what you see here. The Z has to do with the depth. If I look at the Z for this point, all I have to do is look at the points around it and determine if Any of those, if those points are all bigger than this Z, this whole thing's in shadow, right? This Z has to be in shadow. This thing has to be in shadow. If these points are all less than this one, then this one's in front and this one can be seen. Okay? So it's this type of an operation. Once I can determine here, I can determine this point comes back. It doesn't quite lie where I want it to, right? But if all these things are in front, right, then this point can't be seen. And it should be shaded as if it's in shadow. If this thing's all behind, it should be shaded as if it's in front. Yeah, that's the question, isn't it? Right? If some of us is in the front and some of them aren't, well, you know, there's probably been about 45 research papers written about this one. Okay? Some are in the front, some of them aren't. What the first people did was say, if any one of them is in front, I'll say it's in shadow. Right? Why not? Right? I'll just say it's in shadow. The trouble with that is that you end up getting jagged shadows in your scene. Okay, you get very jagged shadows in your scene. You get what we call aliasing on the shadows. And if there's one thing that's really irritating is you have this really nice smooth scene, but the shadows are jaggy, right? It's really irritating to watch. So there are people who say, okay, well then two of them have to be in front, right? You know, and they've played games like this, and you can't quite do it. There's people that have modeled this thing as if it were a surface and then tried to figure out if this is in front. There's all kinds of things you can do. And the bottom line is you can't do it very well. Okay? You can't do it very well. The people at Pixar said, hey, what I'm going to do is I'm going to look around in even a bigger area. I'm going to look around this thing in like a much bigger area out here. Let's see if I got one now. Yeah. So here's a 4x4. 4x4? Yeah, 1, 2, 3, 4, 1, 2, 3, 4. 4x4 area around here. And what I'm going to do is I'm going to look at this point and I'm going to say the following. If all 16 of those things are in front, it's in shadow. If all 16 of those things are behind, it's not in shadow. If 4 of them are in front and 4 aren't, then it's I take only a quarter of the value, right? I diminish it by effectively a quarter of the value, right? So I take this as a percentage, right, or a fraction. How many of these things are in front, how many aren't, to decrease my value. It's a thing called percentage closer filtering, they called it. They gave it a nice fancy name, okay, called percentage closer filtering. It really, what it does is it blurs the boundary out between your alias shadows. That's all it does, is blur this boundary out. And what they found out is in many cases they can make this very big here, do many more than just 4x4, and actually get the shadow boundaries to fuzz very nicely to make them look as if you've got a fuzzy light source, you know, an area light source, not a point light source. They could actually get them out, and they produce some very nice pictures this way. But can you see the process? We take something that we've rendered over here from our camera view. All right, once we figured out something's in front, it's like, okay, now we got to figure out if it's in shadow. So what we do is we project it by our matrices back down into the Zbuffer for the camera, and then we ask in that Zbuffer, is it in front or is it behind, depending on where it is. Okay, and when we map it back, it's unfortunately not going to be on a boundary, so we can't say absolutely, but we can say somehow that it's either in front or isn't in front. Now, go ahead.
So this would also be a good thing to use in parallel, right? Just line by line projecting it.
Yeah, you can write a nice parallel algorithm to do this. Yeah. Okay. So now there's lots of problems with this algorithm, much more than perhaps the jagged shadows that you might get out of this. The biggest problem with this algorithm is what happens if you take a point here, right? You run it back over to here, and it ends up out here, right? Completely outside your depth buffer. Yeah, then you have no information about shadows, right, for it. And so what happens here is if you have to then think about from your light source how big of how big of a camera angle do you give it in order to encompass as much as possible? Okay? How big of a camera angle from your light source? Because if you give it a very restricted camera angle, it'll clip everything out that isn't in that pyramid. Okay? That information won't get into that Z-buffer, and then your points might end up being outside, of which you have no information about the shadows anymore that might be there. And so the difficulty with this is that I have to, if I don't know where my camera, if I don't initially know where my camera is going to be, I have to get a camera angle from the light source that encompasses everything. Okay? Absolutely everything in my scene, because I don't know what's going to be in this eye point range at all. So I have to get a huge, in general, angle to encompass everything. So if I was trying to do shadows in the building, we were trying to do this room, we had the building model, I have to generate my camera Z-buffer from the entire building, not knowing where we're going to put the camera. And this causes really bad problems. Number one, if you put it too small, right, you get maybe your points will be out, and you won't have any shadow information for them. But if you make this really big, what happens is that every one of these cells here is really big, okay? And there are many polygons of your scene that maybe are inside here, inside even one cell. Or if you think about the whole building we're trying to encompass, right? Many of these things might be inside, depends on the resolution of this thing. Many of these things might be in one cell, and then you've lost all the depth information for them anyway, and your shadows come out looking really blocky, it turns out, right, and really bad. And so the problem with this is that you have to know how big to make that camera angle from the light source. You have to know, before you start, you have to know how big to make that camera angle. Okay? And this is a very bad problem. One of the ways that people also get away from this jagged thing is they make the Z-buffer here very big from the camera. They make it a very high resolution Z-buffer, much higher resolution than perhaps even your eye point view. Okay, so that you have a high resolution to generate the shadows from over there. But can you see that you have to know this thing a priori? That you have to know this camera angle in advance? And that's where you get killed with this algorithm, is that, you know, this camera angle could be 180 degrees, right, to try to encompass everything. And then you've got basically a wide-angle lens, and you're in real bad shape, okay? You're in real bad shape. So this algorithm works much better when there's a small thing, right, a small camera angle, and you're in a little local area. Now, one of the things, go ahead.
What if you made it a directed light source, so then you only needed to encompass the angle of the light from the directed light source? Yeah,
this kind of broadened the concept of a directed light source as if it were you could say the light source is a cone shape, right, or something like that. And in that case, you only had shadows, right, from certain angles. And that kind of brought in that concept of maybe we ought to start modeling light sources as having, you know, this limited type of thing. So people do that. Yeah, they do that. But so you can see that this is the case for one light source. What happens with 2, with 3, with 4, with 5, with 6? You've got to do this process every time, okay? And so our initial graphics devices weren't good enough to do this because you need multiple frame buffers. Yeah, you need to keep multiple frame buffers around in order to be able to do it. So you have to have a graphics device by which you can keep multiple frame buffers. Well, in the 1980s, memory was really expensive. People tended to have one frame buffer because it was so expensive. I bought a graphics device in 1980, which was much less than what we have today, for $45,000, right, which had one frame buffer on it. Right, that was it, one frame buffer. And we bought one in the mid 90s that was probably half of what you get on your PC today. We bought it in the mid 90s for $250,000, and it had 4 frame buffers on it. So, you know, these devices were fairly expensive at one point. But this is kind of the culmination of a lot of this, is that Oh, the other point was, if you have to do this over and over again, you need these multiple frame buffers. It takes a lot more time, right? You have to decide for everything that's visible. Fortunately, you only have to do it for everything that's visible, right? So people that tend to use these algorithms tend to do some kind of interesting front-to-back sorts on their data first. So if you start drawing things on the front first, what happens is most of the things toward the end that you're trying to draw are all invisible in the frame buffer, and you don't have to do all this work for them. If you do it back to front, then you keep thinking, as you put a new item in, you think it's visible, you have to do all this work. Each time you put a new item in, it turns out to be, it makes invisible a bunch of stuff behind it, etc. But this is kind of the culmination of all of this transform work that we did in the beginning of the class, right? That you can do inverses on these things too, so that if you're thinking about taking pictures or from multiple angles, you can reconcile all these views together, which is really kind of cool. It's not thought that you can take inverses of all these transforms. And again, the inverses and everything else with all these transforms and all, we build them into one 4x4 matrix, right? So that we can go back and forth very easily. So you can kind of see how this might be done on a GPU. I wrote up probably several years ago a parallel renderer that effectively chopped the scene up. We had some scenes with millions and millions and millions and millions of polygons in them. And what we did was we chopped the scene up, did an octree on the scene, effectively. Okay, we did an octree on the scene, and then basically gave out these octrees to various processors. We dealt them out to various processors and collected a little tiny Zbuffer for each octree, and then kind of started composing them back together. And with the octree, if you start doing the front part of the octree first, okay, can all of you see, if you do the front part of the octree first, eventually perhaps some of these things in the octree that you try to render will have complete coverage on the octree, and you won't have to render anything behind it, right? So you can save some time this way in rendering. Well, what we had then also is we had some shadow volumes to be generated along with it, right? But being that we had these little octree cells where it was guaranteed that everything was inside our octree cells, we could recalculate the depth buffers from the light sources in a very nice way, because we only had to make sure they went around these little octree cells, okay? And so we could limit the angle, get very high resolution shadows, etc. off this thing. Okay, it was a bear to write up this algorithm. 2 graduate students and I did it. And it was an absolute bear to write this thing up and make it work. But once it worked, it was cool, because we could just deal, this is what we've used the CSIF for years, right? We just deal out, things to computers down there and let them go. And we generated some really very, very high resolution pictures. And some of you have seen the railroad cars in my office or something like that. And those were all generated with these with this parallel algorithm. But it was kind of interesting that you had to recalculate the viewing angles and everything from the light sources each time, right, for each individual picture. But you could actually do this while it was done. So, okay, let's see. I think that's it. Any questions with this? Right? This is it's not a terribly hard algorithm to do, but the fact that you have to kind of a priori know how big this angle is before you start makes it so it's, and the resolution of the shadow buffer and jagged shadows has kind of made this thing so it's not used as much as many people would like to use it. So, okay, I am done for today, and you will you'll all be back at 3, of course, and then we will have an exam on Monday. So I will see you then.